I see like a headline pop up every few years about like Zealandia or like
yeah.
is that what we're talking about?
Those New Zealanders will try to claim their own continent, but it's just a bit of Australian.
Hi and welcome to Wonder, brought to you by Geo Co. I'm Holly Cooke, joined as always by my colleague Dr Reid. Today we have the most incredible conversation about the early Earth, the first continents that rose out of the water, and the Earth pulling itself apart into big land masses, coming back together. And basically this notion that the only thing that stays the same on this planet is that it's always changing, and the best way to glimpse that is by looking at our continents. And so today we're joined by Dr Jack Mulder from the University of Adelaide. So we've just had Sandra on the pod. And we went right back to the beginning. We talked about how the Earth was really hot when it first assembled, and basically heat literally makes the world go round. I reckon you've got a couple good claims to old age too. You've seen some old stuff. I reckon you get ancient Earth.
It doesn't look that bad.
Yeah, come on.
I mean, rock claims. What are your rock claims to the old Earth? Can you talk to us about an early Earth?
Sure, yeah. So I've been fortunate to work on the oldest rocks on the planet and the oldest bits of the planet.
I promise I didn't actually know that asking the question. I didn't know that was your answer.
Yeah, so I've done a lot of work in Western Australia. So Western Australia has a really fantastic record of early Earth, some of the oldest rocks and the oldest mineral fragments. So once were a part of some rock and now individual little mineral grains that we've worked on from WA, and they are the oldest things anyone's ever dated on the Earth, and they're about 4.4 billion years old.
Whoa. Okay, so the oldest rocks on the Earth, what does that look like? What's it you've held what did you say how old it was?
The little zircon grains of 4.4.
You've held 4.4 billion years in your hand. What does that look like to hold?
Well, we can't see it because they're kind of microscopic
little
mineral grains.
If you're holding them in your hand, you've done your lab
Pretty
work.
bloody underwhelming.
You've done your lab work wrong if the zircons are in your palm. So what's a zircon? It's a mineral?
Zircon's this little mineral, yeah. It's a tiny little kind of time capsule, so we can date it using kind of mass spectrometry. But yeah, they
date it. What do you mean date?
Hang on.
Let's
Okay.
All right, here we go. Let's whip out the science. What do you mean date?
So we're talking about kind of geochronology here. So minerals contain tiny little amounts of radioactive elements in them. In this case, zircon has a tiny little amount of uranium in there. It's not kind of dangerous to you or anything like that. And that uranium is like a little clock. So it's ticking away and breaking down to different elements, in this case lead, through time. So we know how fast uranium kind of decays. So if we can measure the amount of uranium sitting in these little mineral grains and measure the amount of lead that was produced due to that breakdown of uranium, you can get an age out of your minerals.
And what made the mineral? So 4.4 billion years ago is when we can track to like when the mineral was made, but it had a life before it became a mineral. How did that happen? How did the mineral come to be?
Well, that's one of the big questions. So
Okay.
A lot of debate about where these little zircon crystals actually came from. So a lot of them look like they come from things that look kind of granitic, so kind of felsic looking rocks. Other people think they're coming from more kind of basaltic rocks, so kind of more like things you find on the seafloor today. So it's kind of the opposite ends of the kind of rock
basically
spectrum.
complete opposite type
I was
of rock,
just
aren't
going to
they?
say,
Yes.
here's my question. Why are those different opinions? Are those very different opinions to have? And are they camps of thought? If I'm thinking it looks granitic versus basaltic,
Yeah,
what does that mean?
It has a massive influence on what the early Earth must have looked like. So if these things are actually coming from kind of granites as we know them today, we know granites form in big kind of volcanic arc belts, things like the Andes. So if these things are coming from these kind of true granites, then did we have massive mountain ranges looking like the Andes way back 4
billion
years ago? Or the opposite end of the camp did the Earth not have those kind of typical continental rocks that we can look at and walk around on today? Was it more of kind of a water world where things are kind of underwater and most of it's driven by kind of seafloor magnetism and things like that? So
Amazing.
very different views of what our planet looked like.
Totally. And one of the last questions I asked, and it was kind of a spanner in the works, it sort of jolted the convo a bit, but I asked Sandra and Anthony, then what's a continent? Like after all this chatter about, placing continents back together, like at the end of the day, what's a continent? And I'm sure we'll get back to it at the end, but hearing you talk about like continental sort of, did the world of continents 4.4 billion years ago? What could a continent possibly look like 4.4 billion years ago?
Yeah, look, that's a great question. And what is a continent? I guess it depends what kind of geologist you ask. So a continent means different things to a geochemist or a geophysicist or someone who goes and maps rocks in the field. But yeah, broadly, when we think of continents today, we're thinking of thick bits of the crust that kind of stick out of the water, that are made of lots of different types of rocks, so granites and metamorphic rocks and sedimentary rocks.
Is the defining feature that it sticks out of the water? Or if you take the water away, how could you differentiate continent from everything else?
Yeah, it's a good question. So continental crust, if you're thinking about it in terms of composition, is made of pretty light, buoyant rocks, things like granites. But they don't necessarily have to be sticking out of the water. So there's large parts of the continents that sit underwater as well, but there's still continental crust.
And is that like, I see like a headline pop up every few years about like Zealandia or like,
yeah.
is that what we're talking about?
Those New Zealanders will try to claim their own continent, but it's just a bit of Australia.
You're going to get beat up one day, Jack. Goodness me. So your claim to the early Earth is 4.4 billion year old drops of mineral in WA.
But those are just like little fragments, right? And that's why I said underwhelming, because basically one zircon looks like another zircon. I mean, of course, zircon, morphologists of zircon will debate that, but in principle, they look the same. Mm-hmm. If you spilt them out on the table, you probably wouldn't be able to tell, oh, that's the 4.4 from that's the the one that formed in a granite, which is a million years old. You wouldn't really be able to tell. That's why it's underwhelming. But there are places where you see rocks sticking out of the ground. And I'm really interested because one of the places that you've done field work, and a lot of field work, is up in a place called the Pilbara in the northern part of Western Australia. Maybe you could show us whereabouts that is.
Pilbara, hot part of the country.
It's hot today, isn't it? I mean, Marble Bar is like the hottest town in Australia and regularly get up into the 40s.
Is that Biff country? That's like beautiful red rock country.
Yep. Yeah, it is. Yep, hottest place in the country, and I can attest that their pub has the coldest beer as well. Oh. That might just be relative.
26 lukewarm beers, nothing on 50 degrees outside. Right. So what were you doing in the Pilbara?
Yeah, so
and where,
let's have a look at where the Pilbara is. So here we are.
WA's huge.
WA is enormous.
So here's the Pilbara here. We kind of zoom in.
Right, look at that.
You can see.
Look at that. So Port Hedland, you have there. Port Hedland is one of the biggest iron ore ports in the world. Mm-hmm. So a huge amount of the world's iron ore is mined in the Pilbara region, not in Marble Bar, but just south of that, somewhere around where it says Mulga Downs and those areas there. But this is this really important area, but the Hamersley Range, that sort of place. But in Marble Bar, you can see these really curious structures there. You can see that kind of blobby.
It's all curious. I don't get it.
Blobby shapes with green-looking things in between them. And this is a really fascinating area. A lot of geologists who've studied the early Earth have spent a lot of time crawling over these mountains.
You're saying that's a real pattern. That isn't trees that are sort of randomly dispersed. No. That's a real land pattern.
Yeah, no, those are rocks. So you're looking at.
Why do they look like that?
Well, yeah, that's a really good question. So you're looking at a fragment of one of the first continents on our planet. So it looks really different than the continents we kind of see today. So we don't see any kind of big, long, linear mountain ranges. We don't see kind of rift valleys or anything like that. We see these kind of creamy coloured ovoid zones, and these are granite bodies, and they're separated by these narrow little kind of dark green zones that we call greenstone belts. So those things are made of lava flows and sedimentary rocks like that. So the pattern of this early continent, and the Pilbara is is probably the best preserved early continent that we have on the planet. It looks really different than today's continents.
Does the iron have anything to do with this? Or is that like a story that sits over the top?
No, the iron has quite a lot to do with it. So on the early Earth, there was a lot less kind of oxygen around. So it meant that seawater could dissolve a lot more iron than it can today. And the early oceans on the planet were very rich in iron. And when the levels of oxygen in the atmosphere started to rise throughout the early part of Earth's history, that iron started to drop out of the seawater and form these lovely, big, beautiful kind of banded iron formations.
They're so spectacular.
Awesome.
They are just so spectacular. The whole cliff sides filled with this deep red, steely grey, iron-rich rocks. And you can see some of them, you can see little ripple marks in them. It's just like a beach sand today, but it's just made of iron. It's just incredible. And Marble Bar is really curious because it's called Marble Bar, but the Marble Bar is not made of marble, is it?
No, it's
to a geologist. What is it?
It's kind of chert. Yeah.
What's chert?
What's that?
Chert is a little bit like opal, so kind of microcrystalline silica, basically. Yeah.
A silica ooze that would have
ooze.
formed like on the bottom of the ocean. Right?
Yeah, like a sludgy
kind of stuff that's now.
Righto. So when I sort of offhand said, how can you possibly know what continents look like that long ago? There's actually, kind of relatively speaking, in our own backyard, we've got those early continents, and they're just sitting there at the surface. And what were those greenstone? I feel like I've taken classes where I throw where greenstone belts thrown around. What's a greenstone belt actually?
Greenstone belt, yeah. So they are basically kind of packages of volcanic rocks, so a lot of kind of basalt lava flows and things like that. And quite rarely you get little bits of kind of sedimentary packages embedded in those little greenstone belts as well.
So I've got one more big question. I'm trying to link together with Sandra. We spoke about how heat makes the Earth tick. It's the driver of plate tectonics. But there was a beginning to our Earth. There was a beginning to plate tectonics. Do these continents? What do they tell us about tectonics? When did that come about? Because I assume that as a geologist, we talk about continents coming about because of rocks that are made in tectonic processes. So what does that tell us?
Yeah, look, that's a great question, and it's one of these really long-standing and still active debates that we have in the kind of geological community is what is the birth date of plate tectonics? Has it always operated on our planet? Has it operated at different times on our planet? When did it start if it didn't operate on our planet? So places like the Pilbara Craton, where you see these really unusual kind of geological features that you can't really explain by at least modern kind of plate tectonic processes. It invites the question of, well, maybe these early continents and these early crusts were being produced by some other kind of process. And places like the Pilbara Craton have been really important kind of natural laboratories for kind of trying to understand what those tectonic processes were. And if you can figure out when those kind of processes are happening, you can kind of step forward in time and try to put your finger on, well, where and when do we start seeing things that look more familiar, like the plate tectonic processes and rock types that we see today?
So in the early Earth, we know that it must have been very hot. The fact that Marble Bar is up there now is a coincidence, right? Just
funny.
To clarify. But we know it must have been hot because the Earth had just formed. So all of that heat from the accretion of process of the formation of the solar system and the planets was still like
burning
ball of like a and on top of that we had more uranium. There was more uranium. It was because it hadn't decayed as much. So you had a lot of heat. You had a lot of heat in the system. So my question is, how is heat important in the shapes of these features we see in the Pilbara compared to the linear things you see if you go to the Andes or the Himalayas?
So we're saying when you look on Google Earth and you look in the Pilbara and you see globs and blobs, and then when you look at India, you see lines of mountains, that matters? There's a difference?
Yeah, absolutely. So, the kind of nice lines and mountain ranges that we see on the Earth today mark out boundaries between tectonic plates mostly. So the fact that you kind of don't see them in places like the Pilbara is telling you that the plate boundaries, you're either not in a place that there was a plate boundary or that those plate boundaries didn't actually exist at the time. So, yeah, early Earth is much hotter, so it's much easier for rocks to kind of melt. So you get more kind of voluminous magmatism forming on the early Earth, and different rock types, different kind of densities when they're molten. And in places like the Pilbara, where you get these big kind of granite balloons kind of rising up through those more kind of dense mafic greenstone belts, is a really kind of characteristic feature of a lot of these kind of early Archean continental fragments.
It sounds like tectonics wasn't behaving as it is today.
No,
well, he
it
just
doesn't look like it.
Don't get me in trouble.
No, it wasn't. That's the point, right? Yeah. So are there other places where you see similar shapes in the geology?
Yeah, so you see little fragments of these kind of Archean continents around the world. So places like South Africa, you see them, India, North America, pretty much everywhere you get these really ancient kind of continental fragments. Quite a few of them look a lot like the Pilbara, just not as kind of nicely
exposed.
That's pretty sick.
Yeah.
As a kid, I am young enough to now be saying, like, obviously like had documentaries on BBC and whatever, but also like a YouTube headline that was like ancient supercontinent secrets. Bang. I was watching that content about supercontinents and the mysteries of like how big land masses came together and broke apart. And then it wasn't until I was in geology, I was like, oh, I'm in the space where we learn about this. How did we go from globs and blobs to supercontinents? And again, I asked you what's a continent, then what the hell's a supercontinent? Are they an early Earth feature? Do we have any supercontinents on Earth now? Are you the right person to ask?
Yes.
Yeah, so yeah, I mean, supercontinents, it's in the name. It's a continent that is big. It's super. So it's made of
Real dumb, man. Thanks, Jack.
Cut. We're done.
I do have a degree.
There you go.
We said it. You heard it here.
Yeah. Well, look, that's
big.
what my PhD was in. So I got the credentials to do this.
That's exactly right.
Righto. So big, massive continents, but like it's not like there's big continents all around Earth at that time. It's usually is it usually one? Are there over two supercontinents at a time?
Yeah, it's a good question. So, I mean, probably the most familiar one would be something like Pangaea or Gondwana that people have heard of. And that was a supercontinent that contained most of the continents that we see today. So Australia was kind of stuck on Antarctica and you close up the Atlantic Ocean and North America sits next to South Africa and those kind of things like that.
It's totally rearranged.
Yeah, so totally rearranged now. So those kind of land masses were together about 300 million years ago, and they've kind of broken up and are starting to move around the continent, move around the Earth today rather, and perhaps we're kind of starting to form a new supercontinent.
Unreal.
Well.
So opposed to just thinking like Australia is pretty big, we just saw WA. It's not actually the defining part of it isn't that it's just big land. It's that think about it like jigsaw puzzles that have been pulled together, stretched apart. Oh, not that's wrong, false words. But point is it's not just big land. It's kind of the culmination of processes that have brought parts of the Earth together and clumped it up.
Yeah, that's exactly right. And the jigsaw analogy is fantastic. So like the continents that we see today are just individual little jigsaw pieces of Gondwana, and it turns out that there were probably supercontinents before Gondwana as well, going back to maybe 2 or 3 billion years ago. So it's the same kind of jigsaw puzzle problem, except each time you step back, you kind of throw out half your jigsaw pieces and have to try to piece together what's left.
So Gondwana is made up of bits of an earlier supercontinent, Pangaea, and Pangaea is made up of bits of a previous supercontinent, which has a name like Rodinia, or there's other names, right?
Yep.
And then that supercontinent was made up of fragments of another supercontinent.
Yeah.
So you're saying there's this pulling apart and closing up again, pulling apart, closing up again. But that sort of line of thought assumes that the processes that are moving things together, the subduction and accretion processes, were the same like throughout Earth history. But back to the Pilbara, it doesn't look the same.
Yeah.
So what did plate tectonics, as we know it today, turn on at some point?
Yeah. Well, if you assume that things like the Pilbara weren't kind of produced in a plate tectonic setting, which I think most people would agree on, then
not everybody.
Everybody.
Let's just put a little asterisk there. That there was going to be some people who say, for goodness sake, those guys are on again about.
We've got our little gang.
Yeah.
Vertical tectonics.
Yes, the camps are pretty.
Did you say
well
political
defined.
tectonics?
No, sorry, vertical. No, that's the idea that the modern Earth is more about horizontal processes with things moving together. And the early Earth, because it was so hot, is more about vertical. As Jack said, like buoyancy is more important potentially in early Earth. So that's the idea of things moving vertically.
Yeah.
So, yeah.
Yeah, so the kind of Pilbara style rocks are the oldest bits of it are about 3.5 billion years old, and you can kind of track those packages of rocks down to about 3 billion years, and then you see a really distinct change in the geological record in the Pilbara craton. You go from more of these kind of vertical processes, these big kind of granite plutons rising up, to starting to develop some more familiar looking kind of plate tectonic features. You get linear kind of mountain belts forming in the Pilbara. You get rift basins forming that look a lot like plate tectonics. So that looks like it starts to switch on about 3 billion years ago.
I'm loving this because it's just I like to claim I spend a lot of time on Google Earth. But what I hadn't considered was the patterns of our like landforms, our big landforms being linear structures, and how something as basic as heat, which I think I went for a long time thinking, I'm going to expose myself as an idiot, but like I didn't really think about the impact that heat had on the like.
I agree.
And how it controls forces, and that also means that Google Earth looks different today than it might have otherwise. Like it's just neat. I just hadn't thought about it that much.
No, that's
before.
right. And the heat, I agree with you. I hadn't thought about it much either. I should have, because Sandra McLaren was one of my demonstrators at university days, and she talked a lot. Her and our colleagues talked a lot about heat at the time. But I agree, it's taken me years to come to actually think deeply about. That has a really profound effect on it. One other question I had with you. So, in the terms of these Archean fragments, do you think they were connected at one point as well? If we go back to supercontinent, are they part of another thing, or was there less continent and more ocean at those times?
Yeah, so that's kind of an interesting kind of question. There's definitely less of those Archean fragments preserved today, and that might reflect the fact that there wasn't much continental crust on the early Earth. So there's just like the Pilbara you saw, it makes up kind of a tiny little corner of a modern day continent, the Australian continent, and the other little Archean fragments that we see around the world are pretty similar. They make up kind of small little parts of larger continents. And when you kind of zoom in and look at the kind of geological record of those kind of Archean fragments, a lot of them do look really similar. So the Pilbara is a really nice example. So if you go to the kind of Barberton mountain land in South Africa, you see very, very similar looking rocks to the Pilbara. They're almost identical age, and you can almost match up individual kind of layers in those rock packages next to each other. So it's pretty compelling that things that now in kind of South Africa and in northern WA were once a part of a larger kind of Archean fragment.
Related in some way.
Related in some way. And it's possible that other little Archean fragments are also kind of clustered together, maybe as one kind of big supercraton, early supercontinent, or maybe there were kind of little clusters of them around the world. But yeah, a lot of these early Archean kind of fragments look very similar to one another.
Awesome. I'm just picturing, because that's certainly not the concept of being able to get two continental jigsaw pieces and fit them together in a previous supercontinent. You could do that with just about any rock anywhere on Earth, with how many sort of different times we've pulled apart So I just had the picture of like putting down a piece of string. In my case, I think it was like Nova Scotia, because I think we can relate the rocks of Canada to the Australian area. And if you were to fill the world with all the bits of string, there would be no ground. There would be too many connections. Before we get too much into the jigsaw pieces, because that's a wicked conversation, I wrestled through a paper of yours and I barely understood it, but that's why I want to ask you now, because I've got you captive. But we'll talk about the subaerial rise of continents, and that's the fancy way of, when I picked on you earlier and said, is the water the defining feature of the continents? There was a time when the first continents popped up. How does that happen?
Yeah, absolutely. So
Well, I guess talk about it. I'd love to hear.
So one of the cool things about the Pilbara is when you go into these greenstone belts, so those little kind of narrow sedimentary and volcanic basins that are forming around these granites, when you look at the kind of sedimentary rocks in there that have to be deposited in some kind of water, a lot of them look like they were only deposited in water. So there is no evidence that those bits of the continent were ever sitting above sea level. So you have, particularly for the early history of the Pilbara, for about 500 million years, everything looks like it was underwater. All of the rocks look like they were deposited in kind of shallow, or in some cases maybe quite deep water. When you get again to kind of 3.2 billion years, you start to see things that can only form in either very shallow water or subaerially. So you see things
how do you know what forms on land? How can you look at a rock and not
Well,
form
we
on
see
land?
things like mud cracks. So if you go and look at, a muddy plain or something next to a river today and see little mud cracks forming, those things form in subaerial environments. We can go to the Pilbara and find 3 billion years, and in some cases older, kind of mud cracks that are telling us that little continent had kind of poked its head above the water for the first time.
Shout out to the Pitchy Richie students. That was my first exposure to mud cracks in Adelaide.
Mud cracks, the 3 billion year old mud cracks are pretty impressive. But as soon as you said 3.2, some other little penny dropped in my mind, and that's a really important time for the evolution of life, or at least our fossil record is around about that time. Is there any connection with that?
Yeah, there probably is. So you're right. You do see some very early kind of fossil communities.
Fossil communities? What is that? What fossil? What community?
So life back then in the Archean was basically single cellular, so kind of bacterial life forms. And one really important kind of bacterial family that was alive back then are these cyanobacteria. So they're really good at producing oxygen, so sucking up carbon dioxide or other kind of energy sources from the water or minerals in some cases, and spitting out oxygen. And in the Pilbara, again, is a really spectacular example. You actually see these little cyanobacteria things forming colonies. They're forming coral reefs, basically, but made out of bacteria. And you see them in these really old kind of shallow sedimentary sequences. So it looks like there is a link between these continents kind of rising up out of the water and providing these kind of shallow marine environments that these little bacterial colonies can thrive and create quite complicated kind of reef systems, lots of different morphologies. It's pretty impressive for, single cell bacteria to form these kind of complicated varieties. But there was entire ecosystems forming around these very early continents when they started to pop their heads above the water.
And then the system of continents continues to sort of support or throw life out in our supercontinent cycles. Is that too far a stretch? Is that too far a claim? So as these continents are rising up, we have life starting to go, oh, I kind of like the shallow seas here. And then through time, as we sort of ebb and flow through creating big supercontinents and dispersing them, how does life respond to that?
Yeah, look, that's a fantastic question. And undoubtedly, as we started to grow these early continental fragments into kind of larger areas, you are opening up more space for more diverse ecological communities to start to develop. And that is something that we can actually see in the rock record. And when things like plate tectonics start to kick off and start to produce big mountain ranges that feed sediment flux into the ocean and provide nutrients to these communities, and you see lots of kind of subaerial volcanism starting to influence atmospheric chemistry and things like that. those processes are having a pretty profound influence on what life is doing. So this kind of tectonic cycle that has been operating on our planet has really kind of guided and cradled the evolution of life alongside it.
Brilliant.
I don't really know what to say to that.
Brilliant. No, that's beautiful. Thank you.
Okay, so let's start this jigsaw. What's the first bad boy? What's the first supercontinent, Jack, that we can piece together? And can we do it well? Do we have much evidence for it? And how old is it?
Yeah, so we were talking about the kind of Archean fragments before, and some people kind of group them together into kind of a big supercraton or a kind of family of different cratons. It's probably not quite. And
craton, sorry. What do you mean craton?
Yeah, so craton is just a fancy word early Earth geologists use for talking about continental crusts. So very old, continentally flavoured rocks, old, stable, usually quite cold in terms of their heat flow. So yeah, that's what we're talking about. Craton is early kind of kernels of continents, basically.
Cool. And was it? I want to say no, but I don't actually know anything. I don't know anything about this.
Yeah.
What's the first supercontinent? I want to get
like a list of supercontinents.
Yeah, exactly. What's the first one on my list?
Yeah, well, you better be prepared to kind of cross the mountain.
Yeah,
true.
Depending on who you're talking to.
Yeah,
dangerous
exactly.
science tattoos are dangerous.
Yeah. So we have these kind of clusters of early Archean fragments, and about 2 billion years ago, kind of from 2 billion to about 1.8 billion years ago, it looks like those Archean kind of clusters had amalgamated into a supercontinent that we call Nuna.
Yes.
And it is the first kind of proper supercontinent. And it has a lot of the kind of hallmarks of later supercontinents. We see big kind of collisional zones that reflect these cratons kind of running into each other. We see big rift basins. We see evidence for kind of subduction zones and volcanoes around the margin of it. So it looks a lot like a kind of modern continent, but just larger.
Looks like today's tectonics are at play.
Very much so, yeah.
Incredible. This has just been such a great talk to really illustrate how unbelievably dynamic the Earth is.
Yeah. Like what rings in my head, I reckon it was a field trip you just went on. I reckon the third year field trip, tectonics, which is what you now teach. I didn't have you though. It clicked in my head, the permanence of change. Like I was thinking the only thing permanent on this planet is the fact that it's changing. And the continental story is just like, that's it. That's kind of a heartbeat for it all, is that if you can't even put a pole down anywhere on Earth and definitively say, this is what this is what has always been, and then a million years in the future, this is what will. You can't do that. It's quite
exactly
cool.
Right. And that is one of the awesome things about geology, right? Like there's no other science like it, that you can get an appreciation for the places that we see today haven't always looked like they do today, and have looked very, very different in the past. And that is the record that is written in rocks, and that is such an exciting thing to be able to, sit on a spot in WA and think, hey, I'm sitting on a 3.5 billion-year-old coral reef. Wow.
Yeah.
And it's 35 degrees and cooking hot. Like,
where's my beer?
Kind of different.
Yeah. I was in my little high-vis vest with my lanyards and my looking like a proper enthusiastic third year. And to get it so young, and the great thing for me is we often talk about being time travelers. But how can that be possible when it's 4.5 billion years of time to understand, and only, if you're lucky, a few lots of decades to get there? And rocks is a way of feeling
Absolutely.
like you can glimpse it. And so if I want to glimpse after Nuna, first of all, how does it then rip apart? How do you have Nuna come together, big land, and then you just break it up? How do you break up a continent?
Yeah, really good question. So there is really nice evidence that Nuna starts to rift and break apart maybe 1.5 billion years ago. So it kind of assembles, it sits together for 200, 300 million years maybe. Not much is really happening, a little bit around the edges, but it's kind of a stable, coherent landmass. And then it starts to kind of rift and break apart. So there's a lot of different ideas as to why supercontinents kind of break apart. One idea is that they actually insulate the mantle underneath them, and that heat kind of builds up underneath the mantle because it can't escape under this big kind of continental lid. And eventually you get to the point where you have so much heat sitting under this supercontinent, it starts to kind of break and rift apart.
Right, so it's like electric blankets itself, and that heat.
Yeah, I guess it kind of does.
Throws off the blanket.
You can tell it's on. You can tell. Yeah, right. So it comes together, perhaps in, like you said, many theories. So I don't want to say anything with 100% definitive, but it heats itself up and it starts drifting apart. Why does it? If we talk about in cycles, and I hate to be repetitive, but it kind of is repetitive. Is it when they're drifting apart? Do they just collect on the other side of the Earth? Like, is it how on earth do we get to the next one?
Yeah, that's an
awesome
question.
How do we get to
Rodinia? Yeah. So some supercontinents kind of do that exactly. They kind of break apart, and then on the other side of the world, those continents all kind of run into each other. And some supercontinents are a little bit more chaotic. So only half of it will kind of break apart, and then the other half will break itself apart, and those blocks will kind of travel around for a few 100 million years, and eventually they wind their way back and kind of crunch into the larger kind of block that was left over. So sometimes it's kind of a nice, clean, easy kind of separation, and other times it's a little bit more chaotic.
Bit messy.
Yeah. All right. So, Jack, where in the world have you been where you can touch a rock, slap your rock, and then get on the plane and go to another part of the world and know that you're actually traveling to the same ancient part of Earth? Where's like the jigsaw puzzles? Have you worked in that space?
Yeah, absolutely. And the one that's closest to my heart is Tassie. So I did my PhD down in Tasmania, and there's lots of kind of old rocks in Western Tasmania. They're about 1.5 billion years ago old. They're a part of Noona. You find exactly the same package of rocks in the Rocky Mountains in Montana, Idaho. So I've sat in Tassie on my sandstones, marvelling at the little ripple marks, got in a plane, sat up in Glacier National Park. The rocks are a dead ringer.
Did you see ripples in Glacier?
Exactly. The rocks look exactly the same.
That's awesome. That is very cool. Jack, you've blown our minds. Thank you so much. What an awesome chat.
Thanks, Jack.
Brilliant.